So this project is about addressing the challenges of smallholder farms. So one can ask the question, do these smallholder farms have a future, especially in developing countries like Pakistan? Are they going to continue in some sort of a subsistence activity, or can we provide them some sort of a productive exit, or we can make their businesses profitable? In traditional agriculture, a lot of chemicalization, use of mechanization, GM crops, and now a lot of digitalization. This has led to farmers questioning whether do they have a sustainable future or not. This really leads us to this grand challenge of revisiting these conventional agricultural practices, especially for the small farm prosperity, towards increasing their domestic and global competitiveness, protecting their livelihoods, helping them avoid migration towards urban centers, and most of all, to minimize the environmental impacts of agricultural activity. Now, it is within this context that many farmers around the world, in fact, hundreds of thousands of farmers around the world, are going towards what are known as sustainable intensification practices. These are sustainable agriculture practices that lead towards minimal inputs, maximum outputs, and helping them maintain their land, soil, and water. Now, some of these practices include, for example, raised beds, mulching, intercropping, use of efficient irrigation practices. But really the question is that whether these sustainable intensification practices, do they compete with these traditional agricultural or industrialized agriculture approaches? And this is where our project comes in. What we have done is that we have set up a test bed to help farmers evaluate their practices against the traditional agricultural practices. And what we are doing is that we are using advanced robotic platforms, laser scanners, cameras, and other digital innovation devices to really compare one practice against the other, measure inputs, look at phenotypes, look at the quality of the crops, and help the farmer and the research scientists evaluate whether one agricultural practices is better than the other.
So this robotic platform has been developed while keeping two factors in mind. Number one is modularity and number two is portability. So the assembly is mainly composed of two main components. Number one is the robotic platform itself, and number two is the carrier platform. The robotic platform is developed completely using 3D printed materials. The Jetson DX2 serves as the main brain of the system. It provides us with ample computational power to integrate and interface a number of high-tech sensors. A Velodyne VLP16 has been integrated, which provides us with dense 3D point clouds. A multispectral camera has also been integrated, which records high-resolution images in 6 different channels, which are red, green, blue, infrared, red edge, and thermal. In addition to these sensors, an RTK GPS and an IMU have been fused as well to get accurate localization data. For the robot motion, a cable-driven approach has been adopted. This setup allows us to carry more sensors while following the same path repeatedly, thus giving us very accurate localization data. This robotic platform is helping us achieve a number of research objectives. To accelerate the research in plant phenotyping, there is a dire need of presence of rich datasets available publicly. This robotic system serves as a data collection platform which records high-resolution data and stores it in an efficient manner. The recorded data from the platform is in the form of ROS-backed files, which contains the topics of GPS, IMU, multispectral images, and point clouds from the LiDAR. Each file is tagged with respective time, date, temperature, and humidity information. These ROS-backs are then saved on an online storage portal. To make this dataset publicly available, a network-attached storage is under development, which will serve as a portal of automatic storage. Each scan will be uploaded to the storage automatically after acquisition with a specific naming scheme. Our second research objective is to use LiDAR-based phenotyping to monitor the growth of wheat over its cultivation period. Primary use of LiDAR is to provide 3D structural data of vegetation, which aids in high-throughput phenotyping by eliminating the perception effect that is frequently seen in 3D reconstructions using stereo photography. This can help us acquire a number of canopy features such as leaf area, leaf tilt angle, LAI and leaf area density. With the help of accurate odometry data through GPS and IMU, we can create a feature-rich map of the crop field. This can help us estimate the length of the wheat crops, whereas comparing successive maps can help us estimate the rate of growth of wheat over time. Our third research objective is to perform multispectral analysis on the images acquired through the multispectral camera. The multispectral analysis can retrieve information about the spectrum of every pixel in a captured image with both fine wavelength precision and a large wavelength range. The plant reflection spectra includes data about the physiological circumstances and can be utilized to recover plant biochemical parameters or analyze plant developmental or disease traits.
So the question that may come to our minds is that whether the use of this very, very expensive equipment, would that be deployed really to the farms, or how would this technology really be helpful to the farmers themselves? The purpose of this particular project is not really to have these phenotyping platforms at every farm. In fact, the living lab that we have created on campus, this phenotyping platform is only just one aspect of it. We have done many other innovations where taking cue from these phenotyping like platforms and taking the cue from the data that we have gathered from these platforms, we have rolled out innovations that can be taken to the farmer. For example, soil moisture sensing. For example, looking at on-field NPK budgets and so on and so forth. So really the purpose of this particular project is really to compare agricultural practices and to help them scale up. So scaling up is really the ultimate objective where the end farmer will benefit.